Hi, welcome to lesson 4. This title of this lesson is work, and we are going to discuss what work is and how to calculate it. I'm going to start with a scenario that I have right here. I have a 10 kilogram mass sitting on uh, a floor, and I'm going to start looking at the energies involved or that it has. Initially, at this location, it has a height equal to 0, which means that it has zero potential energy. It also has a velocity, because it's stationary, of equal to 0 meters per second, and which means its kinetic energy is 0, and then so its total mechanical energy at this location is equal to 0 joules. Now I'm going to lift the block from 0 up to 10 centimeters. So I'm increasing the height of the block. And let's relook at the energy at this location. The height is now 0.1 meter. Its velocity, it is stationary still, or it's moved up and then it stops, so it's 0 meters per second. And because it has a height now and still no velocity, then its mechanical energy is going to be just equal to its potential energy, which is mgh. And so if I go ahead and fill in the numbers, mechanical energy equals its mass, 10 times 9.81 times 0.1, which gives me a mechanical energy equal to 0.81 joules. All right, so if we look at this, we see that down here at the bottom, this mechanical energy down at the bottom is 0 joules. We also see that at the top, whenever I lifted the block up, it now has a 9.81 joules. And so the conservation of energy is gone now, because we're not seeing a final energy equal to the initial energy, which means that there is some outside energy that's being transferred into the system, and that's what I'm doing. I am transferring energy from the outside into the system. So I transferred energy into the system. All right, that's what I did. I took energy from myself, from my body, and I used it to lift the 10 kilogram mass. We call this transferring of energy, so transferring of energy is, and it is work. So transferring of energy is work. So whenever we take a system where the law of conservation of energy work is valid, and then we introduce energy into it, we are conducting work or doing work to the system or to the object. There are many ways that I can do work. And here are a few. We've already talked about spring potential energy or elastic potential energy. And so I can introduce energy into a system by stretching or compressing an object. And so it doesn't necessarily have to be a spring. It could be a rubber ball. It could be a rubber band. It could be elastic, something of that nature. But it's stretching and compressing. So stretching and compressing introduces energy into a system, and that's work. Another thing that I can do is I can raise or lower an object. So let's see here. Man, you'd think this would be easy on a computer. Let's see, I can get it. Got it. Okay, good. So I just raised the barbell or the dumbbell, and I have introduced gravitational potential energy into the system. And then the last thing that I can do, or that we can calculate, is I can speed up or slow down an object. That's important. It's either speed up or slow down. It's not change its velocity, because I can cause an object to turn, which should change its velocity, but it doesn't necessarily introduce energy into the system. Instead, I have to actually change the magnitude of the velocity, which is speed. So I either have to speed up the object or slow it down. So vroom, vroom, vroom. I could do this all day. Vroom. All right. Now I want to look at what the calculations for work are. In order to calculate work, we need to make an assumption, and that is that we need to assume that the force required to raise the block in the first scenario equals the block's weight. And let me explain to you why. It might seem to you that that's kind of backwards thinking, because if I were to lift with the same amount of force as the weight of the block, well, then whenever I came up with a net force, well, they would cancel out. And that's true. They would cancel out if I lifted with exactly the weight of the block. But how much over that weight do I really need to lift on the block to get it to start moving forward? Now, I don't want to start accelerating the block. I just want it to move at a constant velocity. So once it gets started, then lifting with the weight of the block and canceling out or having a zero net force would keep it moving at a constant velocity. And it doesn't really require that much force over its weight to get it to start accelerating upwards. And as a matter of fact, if I were just to take this many zeros and then add a 1 at the end, well, that's still more force than the weight. All right, but by significant digits, a lot of these zeros or this zeros on over will go away. So it doesn't take that much to get it to start moving, and then I can just keep using its weight to keep it traveling at a constant velocity. And so that's where this assumption comes in, that the force required to raise the block equals the block's weight. Well, we know the equation for weight, and that is the weight, or F sub g, equals mass times gravity. All right, so it's mass times the free fall acceleration, or the acceleration of gravity. And then we also notice that in the original problem, or the original scenario, that the total energy completed, which was potential energy, equals mg which equaled the amount of work or the amount of energy I transferred into the system. So if work equals mgh, I can start using this to come up with the equation. mg equals fg. So the amount of force that I had to lift up on that 10 kilogram mass, which happened to be 98.1 newtons, is mg. So mg is the force. So work equals force, which is the mg part. And then the other part of the equation, the potential energy equation, is this height. And it just so happens that the height is actually the displacement of the object. And so if I were to draw it there, my red arrow here, well, that signifies the height that I've changed on the mass. And so that is just its displacement, which is delta x. Now there is one thing that we need to keep straight, and that is that these are vectors. Right? Both forces and displacement are vectors, which means that their directions are going to have an impact on how much work is involved or how much work is done. It's really simple, though. We don't have to do any vector calculations. It's just an additional step to this work formula. And it has to do with if I have an angle, or I have two vectors. So let's go ahead and draw a displacement vector, which is red, and I have a force vector, which we'll make blue, and there is some angle between them. And so I can go ahead and say that this angle is angle theta. If there is some angle between my force vector and my delta x vector, or my displacement vector, well, the force, or the component of the force that does the work is the parallel component of the force. So force is in that direction, and the parallel component would actually be about that magnitude in the parallel direction of the displacement. And so if I look at this, then my parallel component actually equals, so force parallel equals my magnitude or the force vector times cosine of the angle theta. And so because work is actually the parallel component of the force times its displacement, I can write that as the force itself times the displacement times the cosine of the angle of the two, or between the two. Let me get back to that. Cosine theta. All right, so I have this new equation for work, and it's really not that hard. F delta x cosine theta. All right, so now I have another scenario down here. I have a 10 kilogram mass sitting on a surface. Let's go ahead and look at the energies involved. So if I were to look at its initial energies, it has a height equal to 0 meters, which means it has 0 potential energy. It has a velocity equal to 0 meters per second, which means that it has no kinetic energy, which means that its mechanical energy equals 0 joules. All right, not a big surprise there. All right, now I'm going to move the block, and I'm going to do work to the block, and I'm going to push it to the right with a 10 Newton force for 10 centimeters. So if I were to look at my equation for work, where work equals force times my displacement times the cosine of my angle theta, well, my angle theta in this case, theta, equals 0 degrees. And so the work that I do is going to equal my force vector, which is 10 newtons, times my displacement, which is 0.1 meters, times cosine of 0 degrees. Now, cosine of 0 degrees is just 1. So I'm left with the work that I completed as being 1 joule. All right, so I did 1 joule of work pushing the block 10 centimeters. Now, let's go ahead and check out what the energy of the block is now. So if I look here, then, well, the height is still 0 meters. The velocity is still 0 meters per second, which means that I have no potential and no kinetic energy. So my mechanical energy equals 0 joules. But wait a minute. We said that energy was supposed to be, or work was supposed to be introducing energy into the system. All right? I'm supposed to be putting energy in, and I did that by moving it. I did 1 joule worth of work, which means I put 1 joule of energy into the system. Why is my mechanical energy still 0? Why isn't the block moving? Can you guess? It's actually quite something that we've already talked about. It is friction. If I'm pushing to the right and the block is moving to the right, well, friction wants to oppose motion. So the motion is to the right, and so I want to push it to the left, or friction is going to want to push it to the left. And by Newton's third law, it's actually going to be equal to, and in the opposite direction of my applied force. So 10 newtons. So friction is actually doing work here. So the work of friction plus the work that I do, so me, equals 0. But what's the angle between the force of friction and the displacement or the displacement vector? Well, the angle is going to be theta equal to 180 degrees. All right, because the force of friction points to the left, the displacement points to the right, and so if I were to do this equation, I would say that work equals the force of friction, which is 10 newtons, times its displacement, which is 0.1 meters, times cosine of 180 degrees. And in case you don't know, cosine of 180 degrees is negative 1. So it's negative 1. So instead of doing 1 joule of work, which is what I did because I pushed in the same direction as the displacement and I had positive work, well, friction pointed in the opposite direction of the displacement and it's going to do negative work. And the work by friction equals negative 1 joules. And if I fill that into my equation up here, the work of friction is negative 1 joules plus the work that I do, which is 1 joules, and you betcha that equals 0 joules. So whenever we have a system where we have friction, then the forces or the work cancels out. And so we have a net work, which equals the net work, sort of like CBS or ABC. The net work is 0 when friction cancels out. And we're actually going to see another energy work theorem that will relate our net work being 0 to the amount of energy in it. Right? And we'll see that later. All right, now I want to look at a scenario where my force is not parallel to my displacement vector. So my force vector is now at a 60-degree angle above the horizontal. So you can think of this as, instead of a 10-kilogram mass, maybe it's a wagon with the handle that goes up at 60 degrees, and I'm going to be on the side of it, pulling on it. And so if I were to move this, pulling on with a force up in that direction to 10 centimeters, well, now I can calculate my, let's go ahead and calculate my work that I do. So the work that I do, so this is the work for me, is going to be my force, which let's say that it is a 30 Newton force. So 30 newtons. So I have a 30 Newton force times my displacement vector, which is 10 centimeters, so 0.10 meters, times cosine of 60 degrees. And it just so happens that cosine of 60 degrees, there's a reason why I picked it, and that is because cosine of 60 degrees is 0.5. So if I were to look at this, the work that I do pushing this block is going to be, well, half of 30 is 15 times 0.10, which is 1.5 joules. All right, now I want to look at a couple instances where the amount of work that we do, or that an object, or that someone does, is going to be equal to 0. I went ahead and wrote out my work equation here, and if any of these terms, such as my force, or my delta x, or my displacement, or the angle between the two, the cosine of the angle between the two, if any of those equals 0, then the amount of work that that object does, or that that person does, is going to equal 0. And we're going to look at a couple scenarios. The one that we're probably most familiar with is, and this is the one that most people think of whenever they think of work, is whenever they try to push on something, or they try to move something and they get real tired and they're just not, it's not working. They're pushing really hard, they're not being able to lift something, or they're pushing on it and it's not moving, but they're getting tired. In physics world, that is not work. The work actually equals 0, because if the object doesn't move, then its displacement is going to equal 0. And so work equals force, displacement, cosine, theta. And so if its displacement 0, well, then the whole thing is 0. So the amount of work done is 0. So whenever you push on an object and it doesn't move, you are doing no work, even though you get tired. Right? There's another common misconception, and that is whenever you carry an object. Yes, you do get tired whenever you carry an object down the hallway, or if it's really heavy, your arms get tired. But your force is actually holding the object off the ground. Once it's moving in the horizontal direction, it does not require a force to keep it moving horizontally. Instead, inertia takes over and it moves itself horizontally. So its displacement is horizontal, but your force is vertical. So your angle between the two, your cosine theta here, is equal to 0. And so whenever that cosine theta or cosine of 90 degrees is equal to 0, well then the amount of work that you do is equal to 0. And then the last scenario I want to look at is, well, let's see, how much work does the planet Earth do to the moon? And so here I've drawn a diagram where we have the Earth and we have the moon, and the force that the Earth applies to the moon is actually the force of gravity, and it points towards the center of the Earth, just like so, the blue vector there. The displacement of the moon, on the other hand, actually points perpendicular to that because it's traveling in a circle around the Earth. And if I look at this, well, then the angle, once again, is 90 degrees. And cosine of 90 degrees is 0. So that whole thing is 0. So the amount of work that the Earth does on the moon is 0. And those are instances where if you don't really think about what the equation is saying, there's a lot of misconceptions with this. Just because you are getting tired or the object is moving does not necessarily mean that there's work being involved. If the net forces are 0, or the amount of force that you apply is 0, but it still has a displacement, well then it still has 0 work on it. If the angle between your force and the displacement is 0, well then there's still 0 work being done.